Well, in our final video in the section called matrix operations or matrix arithmetic, let's multiply these two matrices together. We'll do AB and we'll see if we can also do BA. All right, well actually we've already done several examples like this already. AB, I think we can do this in our heads. Remember, this is a 1 by 3 matrix. Right, 1 row, 3 columns, and this is what? 3 rows by 1 column. So, of course, we can multiply them because this 3 matches this 3, and the resulting matrix is a 1 by 1, or just a simple number. Remember, when you multiply a row matrix times a column matrix, you just get a 1 by 1 matrix, which we usually just write as a single real number. So let's do this in our heads. 0 times 6, negative 1 times 5, and 2 times 3. Add those numbers together. 0 times 6, negative 1 times 5, and 3 times 2. 2 times 3. Okay, I think, I'm going to double check it, I think I got 1. It's a 0, it's a negative 5, and a 6 all added together. 0, negative 5, and 6. So we get 1. Okay, that one was easy. Now let's do BA if possible. BA would be 3 by 1. B is a 3 by 1. And A is a 1 by 3. So can we multiply them? Of course we can, because those two are matching. And then the resulting matrix will be a 3 by 3. So it is very interesting in this problem. We're multiplying two matrices. And whether we multiply AB, we get a completely different sized matrix. And if we do BA, we get another sized matrix that we haven't seen yet. So this one's going to be a 3 by 3. So let's see. BA is 6, 5, 3, that column matrix, times the row matrix 0, negative 1, 2. Oops. And let's see what that's equal to. I know it's going to be a 3 by 3. All right, so row 1 times column 1 gives us what? Row 1 of the first times column 1 gives us a 0. Row 1, which is 6, times column 2 of the second matrix gives us negative 6. And row 1 times column 3 gives us 6 times 2, or 12. Notice in this case, this is simply multiplying 6 by every element in this row. 0, negative 6, 12. And you may guess, well, maybe it'll happen on the second row too, and you'd be right. 5 times 0, row 2 times column 1. 5 times 0 is a 0. 5 times negative 1 is negative 5. 5 times 2 is 10. So we took this row matrix, multiplied every element in it by 5, and that became row number 2. And likewise, we get 3 times 0 for 0, 3 times negative 1, negative 3, 3 times 2, 6. So we took this row matrix and we multiplied it all by 3, and we got this row 3 in this matrix, which is 3 by 3. So let me write down 3 by 1, 1 by 3, we multiplied them, and we got a 3 by 3. All right, let's do one more multiplication example of two matrices. Find AB and BA if possible. So 2 by 2 and 2 by 4 columns. So we can multiply them because these two inner numbers are the same, and the resulting matrix will be 2 by 4, the same size as this one. So let me write down 4, 2, 1, 3 times 0, 1, negative 5, 2, negative 1, 2, 0, 1. Oops, I wrote that incorrectly, row 1. It's a positive 5 and a negative 2. All right, well, let's do the multiplication. We already know it's going to be a 2 by 4, so I will go ahead and Draw the brackets. All right, so this row times this column. First row times the first column. 0 and -2. Add together to give you a -2. 4 and 4 makes 8. 20 and 0 makes 20. -8 and 2 gives us -6. And now we're going to row 2, column 1, 2, 3, 4. So we're going to do row 2 times column 1, column 2, column 3, and column 4. 0, -3. So -3. 1 and 6 makes 7. 1 times 5 is 5. 3 times 0 is 0. They add together to give 5. 1 times -2 is -2. 3 times 1 is 3. So -2 and 3 give us 1. So this is equal to, this is AB, the first product. And notice I didn't give myself much room, but I don't need it, do I? BA, if you put B is 2 by 4, A is 2 by 2, can you multiply these two matrices? You certainly cannot, because these two numbers are not equal to each other. So BA is, I'll say, is impossible to multiply. AB, we already did that one. All right, well, let's look at some properties of matrix multiplication. So A, B, and C are matrices, and D is a real number. And we'll just assume that A, B, and C have the proper sizes that they can be multiplied like this. All right? So, A times B in parentheses times C is equal to what? This is the associative property of multiplication. Remember the associative law, even with regular real numbers. The matrices are going to stay in the same order, but we're grouping them differently. So you put the parentheses around the BC. All right, and then we've got a couple of distributive properties. This will be A times B plus A times C. And this distributive property, we've got A plus B in parentheses and on the left, and then C on the right. So it'll be AC plus BC. And D is just a scalar. So if we want D times A times B, we can, if we multiply the two matrices together and multiply D times every term in it, it'll be exactly the same as if we did D times A and then multiplied by B. Okay, that's the associative property of scalar multiplication. All right, I want to make a comment here. Which would be quicker if I gave you matrices, actual matrices of A, B, and C? Would you rather do this, the left-hand side, or the right-hand side? I'll tell you, the left-hand side is much easier. Adding two matrices is a piece of cake. And then you have one multiplication of matrices, A times whatever matrix this ends up being. Here you have to multiply A times B and A times C. That's two matrix multiplications and then adding them together. And the same thing along with this. This left-hand side would take less time to do. All right, so we are asked here to find, with these three matrices, find A times CB. Now I'm going to write way over here, I'm going to write the dimensions of these matrices. A is 3 by 2. B is 2 by 2. And C is 2 by 2. So notice that we could multiply these two together, and we could multiply these two together because the inside numbers match. That means we can multiply this. So what the property tells us is we're going to go ahead and multiply it just like this. We're going to do CB, and then we're going to multiply A times this resulting product matrix CB, although we would get the same answer if we did AC first and then B. You can do it in any order, in other words, except, well, I shouldn't say it in any order. You cannot rearrange the order of the letters. You couldn't replace A with C, swap A and C or swap A and B, anything like that, because you may not even be able to multiply them in a different order. Don't change the order of the matrices when you're multiplying them. But let's do it based upon these parentheses. Let's first figure out what CB is. CB is a 2 by 2 times a 2 by 2, which we know will give us a 2 by 2 result, a product matrix. So C is 1, negative 1, negative 1, 1. And B is 5, 1, negative 2, negative 2. All right, so that's going to be equal to, all right, first element here, row 1 of the first matrix times column 1 of the second. 5 plus negative 1 times negative 2 is positive 2, so 5 and 2 gives us a 7. This element right here is the row 1, column 2. So we multiply row 1 times column 2 of the second matrix. 1 plus 2 is 3. Second row, come down here. Negative 5 plus negative 2 is negative 7. Negative 1 plus negative 2 is negative 3. All right, that's CB. That's what we have in parentheses. So to get A times CB, we get A, which is 4, 0, negative 3, 5, 0, 1, times CB, which we just computed to be 7, 3, negative 7, negative 3. All right, so let's see. This is a 3 by 2. This is a 2 by 2. So we can multiply them. And we're going to end up getting a 3 by 2, so I'll go ahead and draw the brackets. That should fit. All right, row number 1 times column number 1. 28 and 0. It's 28. Row 1, column 2 of the second one. 12 and 0. Second row, so we drop down to the second row, and we get negative 3 times 7, negative 21, and negative 35. Negative 21, negative 35, is that negative 56? 21 and 35 is, yeah, they were both negatives. So then we get negative 9, negative 15, which is negative 24. Last row, so we're taking third row. We're taking the third row times column 1 and column 2 of the second one to get these final two elements. 0 times 7, 1 times negative 7. Add them up and you get negative 7. 0 times 3 plus 1 times negative 3 gives us negative 3. So this is our resulting product matrix. And just as a reminder, if we would have done it like this, we would have got exactly the same value if we grouped them differently based upon the associative property of multiplication up here.